just make sure we're super solid with this. Let me run through this briefly. Hopefully, if there are any questions, I'll either answer them by doing this, or it'll raise your hand and let me know that you have one. So, a couple of questions here. Number one, when you look at the original question here, how many different bases do you see? There's a specific number. How many? There's 3, right? So there's a base of 5, there's a base G, and there's a base H. So there's 3 bases, and because of the parentheses, this exponent of 3 applies to all 3 bases, not just 1 or 2 of them, but all 3. So the way that I usually note that is I will just draw a little line from the 3 to each of the bases, reminding me that it applies to all of them, not just 1 or 2 of them. All right, so in order to do this, I would need to write 5 cubed. And then my next big decision point is, what do I do with this 3 and this 3? Do I add them? Do I multiply them? Do I go 3 to the 3rd? What do I do? I multiply, yes. So 3 times 3 is 9. So that's G to the 9th. And then just like I multiplied before, I'm going to multiply those 2 together again. So that would be H to the negative 3. So if you got to that step, that's pretty good. It means you correctly applied the appropriate exponent rule. But now we got to simplify this all the way through. 5 cubed is 125. And G to the 9th just remains G to the 9th. But then what does a negative exponent really mean?
Denominator.
Not necessarily denominator, because if it's already in the denominator, negative exponent actually means numerator. So the way I usually put it is, if you got a negative exponent, you need to move the base to the other level. So if it's down, it goes up. If it's up, it goes down. Pretty simple way of thinking, at least for me. I hope that works for you. So because it's a negative exponent on the H has to move down. And when it does, the exponent becomes positive because you did what the negative told you to do. You moved it down. So now it's a positive 3 for an exponent. Okay. Walking around, saw a lot of good answers. Did this raise any questions for you? Is there anything I can do to help? Okay, fair enough. Let's take a look at another one. Let's head back up to the board. Let's look at number 16. Again, we are trying to apply the appropriate exponent rule. And then once we've done that, we'll deal with any negative exponents that are there. I'm open to those ways as long as they're logical, right? If they are, then I'm good with it. But here would be a way that you could do this. To me, this is an efficient way to do this. The first thing I'd look at is in the numerator. I've got 2 different x's. They're both bases. And so if you are multiplying bases, what do you do with your exponents?
Add them.
Add them up. So negative 2 plus negative 4 is negative 6. And so at this point, I have combined the numerator down to just being a single base by adding the exponents. Now, if I am dividing bases, I don't add exponents. If I'm dividing bases, If I'm dividing bases, I subtract the exponents. Yeah. So this would be leaving the base the same, and you always go top minus bottom, or numerator exponent minus denominator exponent. This ends up giving us x to the negative 5, which is a good answer, but the kind of the standard form is we don't want any negative exponents, and so because of that, I need to flip that base to the other level. So this becomes over x to the 5th. And if you ever have a blank numerator, what do you fill that blank numerator with?
A 1.
A 1. So it'd be 1 over x to the 5th. Again, saw a lot of really good answers there. Wanted to make sure that you saw, hopefully, a good example of that. All right, we got one more to do here. This will probably be the most challenging of these review type questions. So, applies to all 3 bases. So I'll put those arrows in there to indicate that. And so maybe my next step could look like this. 2 to the negative 4th, a to the negative 4th, and then what do I do with this exponent and this exponent? Base to a power to a power. You multiply, yeah. So if you have a base, which is a b, and that base has an exponent, and then there's a whole other exponent on that, like this situation, that's when you multiply your exponents. Negative 4 times negative 4 is 16. So for folks that had b to the negative 8, that tells me that you added your exponents when you should have been multiplying your exponents. Okay, so then kind of the final step here is to look at all your bases and ask yourself a really simple question. Does the base have a positive exponent, or does the base have a negative exponent? And if the base has a positive exponent, it needs to stay where it is, right? But if the base has a negative exponent, it needs to flip to the other level, either down to up or up to down. They're all in the numerator, so there's going to be only flipping down if it happens. So with this one, I look at my fraction and I see that first base is 2 to the negative 4th. That's a negative exponent, right? So it needs to drop down. So 2 to the 4th in the denominator. The a, same thing, right? It's got a negative exponent, so it has to drop down. So it's a to the 4th down there. The b has a positive exponent, so it stays exactly where it is. Final step would be to realize that 2 to the 4th is 16. So Sam, I think you had that one. B to the 16 over 16, a to the 4th. You were just asking me there at the end, and I think, yeah, right? You got it. Yeah, nice work. Okay, so of the three, to me, that's the most challenging as far as the complexity level. I think you might agree with me there. But before we move on and leave this, do you have any questions?
Is this our last example on like the boards for today?
For this stuff, yeah. This is just review from the last couple of days.
Yeah.
But the good news is we'll do more of this tomorrow for sure. We'll spend about half our class tomorrow doing this. Okay, we all settled? We good? Okay, fantastic. Why don't you grab your notes? We're going to do a little bit with scientific notation today, and that'll be that. I am banking on the idea that you've heard of this before, maybe in a middle school science class or maybe a middle school math class. I'm hoping that you've seen this, or maybe even a high school science class. Maybe you've seen this a little bit. So what is scientific notation? Scientific notation is this form right here. It is some number times 10 to the a, and the 10 is a very specific number. Let's talk a little bit about the n. The n has to be between 1 and 10, but not including 10. So in other words, it has to be less than 10, but greater than or equal to 1. Right? So some examples of numbers that would work for n would be things like 2.3. Do you see how that fits? Another example would be 7.8. Another one would be 1.6429. That fits, doesn't it? These would be examples of numbers that don't work for n. 12. Yeah, 12 is outside of that domain, isn't it? 0.6 is outside of that domain. Here's a tricky one, 13.9. It's got a decimal in there, so sometimes people will think that that would be a good number for the n, but it's bigger than 10, isn't it? So that doesn't work either. So that n value has to be between 1 and 10, but not including 10. Make sense? Okay. And then 10 is going to be the 10 power. This is going to allow us to move the decimal around. Maybe you remember that. And then, of course, a is the exponent. And that exponent is going to tell us the direction that we would move the decimal and how far we'd move the decimal. What's the point of all this? Do you guys know? Like, why would anyone even bother with scientific notation? Yeah, Anna.
If you have an outrageously large number,
Yeah.
like 1 million.
Or how about 20 trillion? Or how about a 5 with 20 trillion zeros or something? Yeah. A ridiculously huge number. Or a really tiny number, yeah. So if you've got either one of those, then scientific notation just might be the thing to allow you to compare it with other numbers or use it in a more easy way, or not have to write 50 zeros after some number, right? That makes no sense. And so easier notation would be scientific notation. So huge numbers, tiny numbers, that's the point. So listen, I'm very aware of all, or at least most of the different ways that teachers will teach this and students will learn this. I have my way that I like to remember this, and so I'm going to try to teach you that way. If you have a way that you like, that's great. But a lot of times people have a difficult time remembering which way to move the decimal point and all that stuff. And I just want to give you a consistent pattern. All the rules that you see in books tend to get confusing because it's all about pluses and minuses and lefts and rights, and it's easy to get them mixed up. And so I'm going to try to boil it down to just 2 ideas instead of like 4 or 8 ideas. So if you guys would look, number 1 here, and I apologize for the notation. I know it's a little bit awkward. This is number 1, and the number we're looking at is 9.03 times 10 to the 7th. So please don't let the 1 and the 2 confuse you. So 9.03 times 10 to the 7th, that number is in scientific notation, and our job here is to write this into standard notation. So here's what I'm going to do. I'm going to take that 9.03, and I'm going to write it off to the side, and I realize that I'm going to need to move that decimal to the right or to the left in order to turn this into a standard form number. And here's the system that I like to use. I am going to look at this exponent of 7, and I'm going to recognize that that number is positive. So if that exponent is positive, that means that my number is really big. So if you've got a 10 power that's positive, that means that I've got a large number. So if I was going to turn this 9.03 into a large number, which way would I have to move the decimal point? To the right. Yeah, so I'm going to move it to the right, and I'm going to move it to the right 7 times. So it's going to be 1, 2, 3, 4, 5, 6, 7. You guys remember what goes in all those blank spots? Zeros. Yeah, all placeholders there. So fill those empty places with zeros. So this ends up being, let's see here, 903, and then 1, 2, 3, 4, 5 zeros. This ends up being 90,300,000. Bless you. So if you can follow that, that idea of big numbers and small numbers as opposed to positives and negatives and lefts and rights and all that stuff, to me that's easier. Just think big number, small number. So another example here, number 2. Maybe you notice the exponent's negative. So if the exponent is negative on one of these, that means the standard form number is really small. Okay, so if I was going to take this 6.2 and I was going to write it in standard form, but I know that it needs to be a small number, which way do I move the decimal? To the left. Yeah, so I'm going to move it 5 spaces to the left. So that would be 1, 2, 3, 4, 5. And as before, I'm going to fill those empty spaces with zeros. So then I end up with 0.0000062. Again, small number goes with the negative exponent on the 10 power. Okay, so I want to see if you guys can go the other way here. So let me flip over to this next page. Let's do this one right here. So again, I apologize for the way this looks. That's just number 3, right? So let's see if we can turn this into scientific notation. This is going the other way from what we just did. This is currently in the standard way of writing a number, and I want to put this into scientific notation. Keep in mind that that number, the n, has to be between 1 and 10, not including 10. So what I would do with this here is I would automatically write 4.2, right? That's the only way I can arrange this so that that number is between 1 and 10, not including 10. But now I need to go times 10, bless you, to the something. How many places do I need to move that decimal to get it between the 4 and the 2? 1, 2, 3, 4, 5. You're right, 6. Now, we got to decide, is that 6, is it going to be a positive 6 or a negative 6? And here's how I like to answer that. I look at the original number, the standard form number, and ask myself, is that a really big number or a really small number? It's very small, so the 10 power needs to go down to being a negative, right? It needs to drop down, get smaller. So negative 6. Okay, still hanging in there? Again, like I said, I'm banking on the idea that you've seen this before in middle school or some science class, whatever, and we're just kind of going with that. All right, so then number 4 and number 5, these are both not in scientific notation. So if you guys would, let me just I'll give you a couple minutes to try these by yourselves. Try to put these into scientific notation. Let's hear from you guys. So for number 4, anybody want to volunteer and answer as far as what you think the scientific notation, Grace, would be?
5.367 times 10 to the negative 9.
Times 10 to the negative 9th. Okay, what do you guys think? Good? Bad? Close? Way far away? Jake, what do you think? It's a positive 9. And were you going to say the same thing, Paige? Okay.
That's what I meant.
You meant positive 9.
Yeah.
Why do you guys think it's positive 9? Can you give support for that? What do you think, Ashton? It's a big number, yes. So a big number, when you put it into scientific notation, the 10 power should go up, not down. So 10 to the positive 9. Okay, and then number 5 was a little unique. Doesn't number 5 almost look like it's in scientific notation? Why is it not? Yeah, it's not between 1 and 10. Yeah, so the 783 is too big. And so anybody want to volunteer a thought on this as far as what you think the scientific... Yeah, go ahead, Joel.
Move the decimal over 2 places and then add 2 exponents.
So move it over, so 7.83. So now it's between 1 and 10. And then what do you do with the exponent?
You add 2 power to 8.
So 10 to the 10th? Mm-hmm. Yeah, so the reason why we add the 2 is because, of course, 783 is a big number, right? it's bigger than 10. And so you're going to make that 10 power go up. Okay, last thing I want to show you guys is how to deal with this on the calculator. There's some cool stuff on your calculator you may or may not know about. So if you could get your calculators out, we'll at least do one of these. Maybe we'll do both. We'll see how much time we have on your calculators. Let's see here. I'll do it this way. Okay. There we go. This will work out. Okay, check this out, please. On your calculator, can you guys find the and this is for the TI-84 type calculators. If you got a different one, I think for a lot of the TIs are the same way. You guys see the 7, and right above the 7 there's a comma. Do you see how above the comma there's a little blue option? It says EE. Look at your calculator. Mine up there, it's going to be really tiny, and my mouse doesn't show up. So here, you see the button that just turned red? Right above it, it should say EE. Make sense? You see that? Okay. So EE means times 10 to the blank. So EE simply means times 10 to the something. And so this allows us to do scientific notation. So for example, I realize I'm a little bit off that screen there. I think this will work out okay. So number 6, this is a big multiplication problem, and we might do this with scientific notation. Let's take a minute here. Let's take this number right here, and can we write that in scientific notation? So let's do that. It's going to be 2.4. That's going to get us between 1 and 10. 2.4 times 10 to the, I don't know. Is that what it is? 1, 2, 3, 4, 5, 6, 7. Yeah, it's 8. So -8 because it's a tiny number. And that other number is huge, right? So it's going to be 5.31 times 10. This will be a little bit easier, right? 3, 6, 9. What do you get? 12. Okay, so we're going to do this on the calculator. Here's how you do this on the calculator. By the way, there's a video going on right now, so if you forgot these button pushes, you could always go back here in a minute and watch the video and get this. Okay, so in order for me to use the calculator, some of this has to go away, so let me do this and this. Okay, so let's see here. It was 2.4, wasn't it? So check this out. 2.4, standard 2.4 as normal. And then if you want to do times 10, it was 10 to the -8, wasn't it? Yeah. So it'd be times 10 to the -8. We're going to go second EE. So notice I didn't push times. Notice I didn't push 10. I don't need to because E simply means times 10 to the. Make sense? You want to use this button. You want to use this button. So, and I put in -8, so -8 goes right there. The way we would read that right there is not 2.4 E -8, it's 2.4 times 10 to the -8. Let's finish this up. The other one was, so it was times, and it was 5.31 times 10 to the 12th, so I would just go E12. So that's basically the calculator representation of what we have on our paper. At this point, all you have to do is push enter, and it'll give you an answer, 127,440. And the calculator obviously did all the heavy lifting for us. Okay, so I think what we'll do, since we're running out of time right here, I think tomorrow one point or another. We'll do number 7, give you another chance to practice with the calculator. That'll probably be good. Otherwise, I think we're done.